Hi everyone, welcome to Learn for Excellence, Learning Made Easy by Abdul Mishan Ahmad. Today we are going to discuss some problems on heat exchanger. Before going to check the methodology of heat exchanger, first we'll check it out what are the process conditions required. So process conditions that are required are T1 and T2, those are the inlet and outlet temperature, W, C, S, mu, K, RD, that's the dirt factor, and at last pressure drop. So here we are going to solve problems till dirt factor. So after reading the question, first duty is to take the exchanger data. So first we'll take the exchanger data on shell side, that is nothing but internal diameter or inner diameter, baffle space and number of passes. So if number of passes are not given, we have to take the number of passes as 1. Next, while talking about the tube side data, first we have to take the number and length of the tubes, outer diameter, BWG, pitch and number of passes. After taking all the details, first step in solving the problem will be finding the heat balance. Heat balance can be found out using the formula Q is equal to WC T1 minus T2. Here capital letter W and C represent it is for shell side and small letter W and C represents for the tube side. C here is nothing but specific heat and it can be found out from figure number 4 at average temperature. Average temperature of the hot fluid will get C for the hot fluid, and if you are talking about cold fluid, you are going to take the average temperature of the cold fluid. Next, after that, the next step will be true temperature difference, that is delta T. So in order to find out true temperature difference, we need to find the LMTD here. LMTD is equal to delta T2 minus delta T1 divided by ln of delta T2 by delta T1. Next, after finding LMTD, we are going to find the value of R and S. The formula for R and S is given over here. That is nothing but T1 minus T2 divided by T2 minus T1, and S is equal to T2 minus T1 divided by T1 minus T1. So here 1 represents the entry fluid temperature and 2 represents exit fluid temperature. After finding the value of R and S, we need to find the value of Ft from figure 18. Now look at this figure over here. So we'll be having the value of S, which is over here, and we'll be knowing the value of R. Now look at the values of R. From this R values and from this S value, we need to find the value of Ft. After finding the value of Ft, we need to find the true temperature difference, that is nothing but delta T. Delta T is nothing but log mean temperature difference, that is nothing but LMTD, which we have calculated. LMTD into Ft we need to calculate. So Ft, which we have calculated from this figure using this R and S. Next, after finding this delta T, or we can see it as like true temperature difference, the third step is like finding the calorific temperature, Tc and small tc. So in order to find the calorific temperature, we need to take the temperature difference of the cold fluid and temperature difference of the hot fluid, that is nothing but delta T1 divided by delta T2. Next, after finding this, we need to find the value of Kc from figure 17. Now look here. Here we'll be having Kc. In order to find this value Kc, we need to know temperature difference. We need to know the temperature difference. What is this temperature difference? T1 minus T2. It is in capital, or we can say it as like hot temperature difference we need to take, and using that hot temperature difference and API gravity. API will be given anyways. So using these two values, we need to find the value of Kc. That is nothing but Kc factor. So after finding this Kc factor, we'll be having this Kc factor and we'll be having this delta Tc divided by delta Th. From this we can find Fc. So after finding this Fc, we can substitute the value of Fc in Tc, that is nothing but calorific temperature, using Tc is equal to T1 plus Fc into T1 minus T2. Similarly for the cold fluid, using T1 plus Fc into T2 minus T1. Next, fourth step will be finding the flow area. Now from this step on, we'll be having two parts: flow area, or whatever the values we are going to calculate for the shell side, and the next one is for the tube side. Now we'll look at the shell side. Here we'll be having flow area, that is nothing but AS, AS, area of the shell. Okay, so AS is equal to ID, internal diameter of the shell, into C dash into B divided by 144 into PT. PT is nothing but pitch length. So how to calculate this C dash? C dash is nothing but pitch minus outer diameter. Next, cold fluid tube side. So here we are going to find the flow area using the formula A is equal to number of tubes into flow area per tube divided by number of passes. Here we'll be knowing with the number of tubes and number of passes, but flow area should be calculated or should be found out from table 10. So while solving the problem, we'll go through it and we'll check it out how we are going to check the value from table 10. Next is mass velocity. Fifth one is mass velocity. Mass velocity is nothing but ratio of W divided by A. If it is a cold fluid, we are going to take the value from cold fluid. If it is a hot fluid, we are going to take the flow area from hot. That is nothing but AS. Next is finding the Reynolds number. So Reynolds number is equal to, it is given by RE is equal to dE into GE by mu, or we can say dE into GS divided by mu. Here d into GT divided by mu. It is GS is for shell side and GT is for tube side. Okay, so in order to find the value of mu, we need to find the value of X and Y from respective fluid. X and Y value of respective fluid from page number 829 and 830. So using X and Y value, we can calculate the value of mu in centipoise, which is given in figure 14. So after finding the value of mu in centipoise from figure 14, we need to multiply it with 2.42. Because it will be in centipoise, we need to convert it into SI unit. So final value of mu will be, mu is equal to mu centipoise value into 2.42. Look here, we'll be knowing the X and Y value from page 829 and 830. Look at this X and look at this Y. We'll get some intersection point. Let us assume if the intersection point is over here and the caloric temperature in Fahrenheit, if it is given as 200, so we'll connect this point and this and we'll produce the line to get the value of mu in centipoise. So after finding the value of mu in centipoise, we need to multiply with 2.42. Clear? Okay, after finding the value of mu, we'll be knowing the value of GS. Now the next part is finding the value of DS. Now in order to find the value of DS, we need to go to figure 28. So now look here, so in order to find the value of DS here, we need to know the diameter and the pitch length. Now look here, here we'll be knowing the tube diameter and we'll be knowing the pitch length. From this we can directly calculate the DS over here. Look here, I'm moving the mouse cursor over here. So look at this, from this we can calculate the value of DS. Next is to calculate D for the tube side. Sorry, for the shell side. Next is to calculate the value of D for the shell side. Next is to calculate the value of D for the tube side, and in order to calculate the value of D for the tube side, we need to go to table 10 with the help of BVG and outer diameter of the tube. I'll show you the sample picture of the table over here. So outer diameter will be known over here. So after that we'll be knowing the BWG. So let us assume that if the outer diameter is 1/4 inch and BWG is 13, then D will be 1.08. Next, after finding the Reynolds number, if the Reynolds number is less than 10,000, we need to go with one more step. That is nothing but finding the value of L by D ratio. So if the Reynolds number is less than 10,000, we need to find L by D ratio to find JH. Next, JH for shell is calculated from figure 28. because shell side heat transfer curve for bundle. So if you are going to find the value of JH for the tube side, we need to go for figure number 24, because JH for tube side can be calculated from figure number 24. Now in order to find the value of JH, we'll be knowing Reynolds number over here. So using this Reynolds number, we can produce the line directly upward to get the value of JH here. So after getting the value of Reynolds number, it is very easy to find the value of JH here. Next is JH for tube side. Now look here, majority of the times L by D, or we can say Reynolds number, will be more than 10,000 for the shell side. Sometimes it will be less than 10,000 for the tube side, but shell side it will be more than 10,000. Now if you are talking about L by D ratio, like if the Reynolds number is less than 10,000, we need to find the L by D ratio. So with that we need to find JH. Now look here, so why we need to find here L by D ratio? Because after the line crosses, or after this 10,000, the line will be almost single. The Reynolds number line, look here, look at this, okay, Reynolds number line will be almost a single straight line. So before 10,000 we will be having multiple number of lines. So in order to get the proper line or the exact line, we need to find the L by D ratio here. So with this L by D ratio and the Reynolds number, let us assume Reynolds number is like 4,000, and 4,000 will be over here, and L by D ratio is like 20 or something, so it will be here. So it will vary accordingly, and horizontal value of this JH has to be calculated. Next, after calculating this, we need to compute the value of C mu divided by K whole to the power 1 by 3. So we know to calculate the value of C, we need to go to figure 4, and in order to calculate the value of K, we need to go to figure 1. So in order to evaluate the value of C, we need to know JH. That's already solved in the equation 7, or we can say the step number 7, and API will always be given in the question itself. So we'll go to figure number 4. Now look at this. In this figure number 4, we'll be knowing the API value. So with this API value, we can alter the line, whichever we want. We can take the line, and from this line and the temperature, we can calculate the specific heat. That is nothing but C. Next, similarly from figure 1, temperature is over here, and the API we can calculate K here. So C and K can be calculated with the help of these two figures, that is nothing but figure number 4 and figure number 1. After finding the value of C and K, we need to find the value of H naught, because we'll be knowing mu, we'll be knowing C, we will be knowing K. So the whole value C mu by K whole to the power 1 by 3 will be calculated easily, and the value of C and K will be same for both shell and tube side, but mu value will change, because of which the C mu by K whole to the power 1 by 3 value will also vary. Now next step is to calculate H naught. That is nothing but corrected coefficient. So in order to calculate H naught, we need to find the value of JH K by D C mu by K whole to the power 1 by 3 divided by phi s, or the shell side. If it is the tube side, it will be phi t. So we'll be not knowing with the phi s and phi t. So what we'll do is we'll find the ratio of H naught by phi s and Hi by phi t. So all the other values are given over here, so we can calculate it easily. So till now we know how to calculate the value of H naught and H naught by phi s and Hi by phi t. After finding the value of H naught by phi s and Hi by phi t, we will go to tube wall temperature. So in tube side, before going to tube wall temperature, we need to find the value of Hi naught by phi t. Hi naught by phi t. Here Hi naught is nothing but corrected coefficient. So here we need to find the corrected coefficient ratio. This Hi naught by phi t is equal to Hi by phi t, which we have calculated in the previous equation, that is nothing but step number 9. From there we are going to take the value of hi by phi t and we are going to multiply with internal diameter and the outer diameter inner diameter and the outer diameter. So if you are going to multiply this, we are going to get the value of corrected coefficient. So after getting the value of corrected coefficient, we'll calculate the value of TW. TW is nothing but TC plus H naught by phi s divided by HI naught by phi t plus H naught by phi s into TC minus small tc. So TC and TC are the calorific temperature of the hot fluid and the cold fluid. Clear? So this tube wall temperature will be common for both shell side as well as hot side, or we can say shell side as well as tube side. Next, the 11th step will be finding mu W. And the next 11th step will be finding mu W and phi s for the shell side and mu W and phi t for the tube side. So if you are going to find the value of phi s and phi t, we can calculate H naught and HI naught, right? So in order to find the value of mu W, we need to again find the value of x, y. Similarly, how we have calculated for mu, we need to take the value of x and y from figure page A29 and A30. This I have shown you. If the fluid is kerosene, we can take the value of x as like 11 and 16. If the other fluid is like mid-continental oil, crude oil, then we can take the value of x as 10.3 and 21.3. Similarly, okay. Next, if it is some other liquid, we can calculate or we can find out the value of x and y from this figure. So we'll be having two different figures here, so we can calculate the x and y based on the given condition of the question. So after calculating the value of x and y, we are going to find the mu W at tube wall temperature. The previously we have calculated mu W. At that time there was no tube wall temperature, so we are going to take the mu W, or we are going to find the value of mu W at average temperature. So now after getting tube wall temperature, whatever the value we are going to use, we need to find the ratio, or we need to use the graph with the help of tube wall temperature. So similarly, as we have discussed previously, to find the value of mu, that is nothing but centipoise value of mu into 2.42. Similarly, we are going to use the same thing. Next, after finding the value of mu W, we are proceeding to find the value of phi s and phi t. This can be calculated from figure number 24. Now look here, we'll be having Reynolds number, we'll be having L by D. So if the value is more than 10,000, no need of L by D. Anyways, the value of shell side Reynolds number will be more. So here we'll be knowing mu by mu W. So from figure number 24, not this one, this one is used to calculate the value of J. This one is done, right? So in order to find the value of mu is over 5 is over here, sorry. In order to find the value of 5, we can calculate the value of 5 with the help of mu by mu W. Take the value of, search the value of mu by mu W, like evaluate the value of mu by mu W, take the vertical line and take it horizontally, you will get the value of 5. So if the value is not given, so sometimes we can calculate it directly. If it is like no need to look at the graph, because the value will be almost similar, so we can take the value of 5 as mu by mu W whole to the power 1 by 4. But if you want to get the exact value, it's better to go with the graph. That is nothing but taking mu by mu W and finding the value using the graph. Okay, so now we'll be getting the value of phi s and phi t. After getting the value of phi s and phi t, we are going to put it in corrected coefficient to get it as like h naught by phi s. We will be knowing anyways, so multiply by phi s, we'll get the corrected coefficient. Similarly in the tube side also, so we'll get h naught and hi naught, that is nothing but corrected coefficient on the shell side as well as the tube side. After finding that, we are going to calculate the clean overall coefficient UC using the same formula, that is nothing but hi naught into h naught divided by hi naught plus h naught. So after that, we are going to calculate the design overall coefficient, that is UD. UD is equal to Q by A delta T. Q will be common for both the values, so again no different thing over here. So design overall coefficient will be only single value. So at last, like 13, 14 and 15 will have single value. No, there's no difference between like shell side and tube side. It's a common value. So Q divided by A delta T. Delta T is nothing but corrected temperature difference, or we can say like true temperature difference. Next, after finding the value of design overall coefficient, we are going to, like, in order to find the value of design overall coefficient, we need to know heat transfer area. Heat transfer area A is given by A double dash L into NT. L is nothing but length of the tubes, NT is nothing but number of tubes, and A double dash can be calculated from table 10. So after calculating the value of A double dash, that is nothing but external surface area per inch per feet. So after calculating that, we are going to find the value of dirt factor, that is nothing but RD. That will be the final step. So RD is equal to UC minus UD divided by UC into UD. So UC will be knowing over here and UD will be knowing over here. So we are going to find the value of RD. So at last we need to check the comparison of RD which was given in the question and which we have obtained. So if it is not closer, we need to check the pressure drop again. So that we'll discuss in the next session. So this is a methodology to calculate or to solve the problem on heat exchanger. Thank you. Thanks for looking at the video, and for more updates, subscribe to our YouTube channel and don't forget to hit the bell icon. Thank you once again.